So good morning everyone. Today we will learn about image enhancement. So what is image enhancement? Image enhancement is nothing but process of manipulating the pixels in the image. Process of manipulating the pixels in an image so that result is more suitable than original one. Suitable than original image. Okay, so what does it means? So what is image enhancement? If you modify the pixels, what happens? Simple. So need of image enhancement. Need of image enhancement. So if you manipulate the pixels, what happens? First thing is it improves the quality of the image. Okay, quality of the image for human perception or human vision. Human perception. Okay. How can we achieve image enhancement? First thing is by suppressing the noise using filters. Second one is by modifying the brightness and contrast of the images, right? So generally, how can we perform image enhancement? So image enhancement mainly done in two domains. First one is spatial domain. Second one is frequency domain. Means modification done directly on image itself. Spatial domain means image plane itself. Okay. Frequency domain means modification done on frequency components of image. Frequency components of image. Okay. So spatial domain techniques are classified into three types. Okay. Spatial domain techniques are classified into three types. Point, local, global. Okay. Frequency domain universal bus, we have low pass filter and high pass filter only. Okay. In that we have one more, that is band pass, band reject. Okay. So point processing, local processing, global processing. So what is meant by point processing? Each pixel is modified individually. Modified. Local processing means neighborhood pixels. Neighborhood pixels are modified. Modified. So local processing is also known as masking operation. Okay, masking operation. And third one is entire pixel, entire image is modified. Sometimes global techniques are also referred as point processing only because each pixel modification is done here through entire image for entire image. So global processing sometimes is referred as point processing also. So image enhancement is simply defined as S is equal to some transformation to the input image where, okay, S is enhanced image, R is input image, T is some transformation or some modification applied to the input image. Okay, so in point processing we have three techniques: modification of brightness, modification contrast adjustment, and third one is histogram manipulation. Histogram manipulation. These three techniques are available in point processing. In local processing, we have three techniques. One is low pass filter, second one is high pass filter. Okay. In low pass filter, again we have so many techniques. Mean filter or average filter. Another one is weighted average filter. Weighted average filter. Next one is Gaussian filter. Next, Bartlett filter. Okay. Next, median filter. Out of these, it is non-linear filter. Remaining all are linear filters. In high pass filter, we have unsharp masking, high boost filtering. High boost filtering. Okay. High boost filtering. Next, in global processing, again we have linear, non-linear. So in linear we have image negative. Image negative. In non-linear We have logarithmic, exponential, power law, contrast stretching, bit plane slicing. Bit plane slicing. Next, intensity level slicing. Okay. In LPF, HPF, BPF, BRF, we have same terms. First one is ideal. Second one Butterworth. Third one Gaussian. So ideal LPF, Butterworth LPF, Gaussian LPF. Similarly, ideal HPF, Butterworth HPF, Gaussian HPF. Like this, we have terms. So this is the introduction to image enhancement. In that, first we will learn about image enhancement using point processing. So point processing means, suppose this is image. So each pixel we have to apply transformation function. Means each pixel is modified. Each pixel is modified. Okay. In that, first one is brightness modification. The transformation function is given as S is equal to R plus R minus N. Okay, R plus R minus N. Okay. Enhanced image. R means input image. N means some constant. Okay, some constant. So if you perform plus operation, brightness increases. If you perform minus operation, brightness decreases. Okay, brightness decreases. Second one is contrast adjustment. Here also the function is defined as S is equal to some R into some constant. Okay, into constant. If K greater than 1, contrast increases. If K less than 1, contrast decreases. Okay. Third one is histogram manipulation. Okay, this is very important. Here we modify the histogram of an image. Okay, so what is histogram? What is histogram? So histogram is defined as h of rk is equal to nk. What is mean by rk and nk? Rk means kth intensity level of n-bit image. And nk is number of pixels with intensity level rk. Let us take one example. I am giving one image, 3-bit image. Okay, 3-bit image. 3-bit image means the range of image is 0 to 7, right? So I am giving 3-bit image like this. 1, 1, 2, 3, 4, 4, 5, 6, 7, 7, 5, 0, 2, 1, 0, 3. Okay. This is a given input image R. Okay. So for this 3-bit image, possible intensity values are what? 0 to 7. Right? So I am writing RK now. RK. So 0, 1, 2, 3, 4, 5, 6, 7. Now I have to calculate histogram. H of RK, that is equal to NK. What is meant by NK? Number of pixels with intensity level RK. Now what is the intensity value here? 0. In the given image, how many zeros are there? 1, 2. Next 1. How many ones are there? 1, 2, 3. How many twos are there? 1, 2. How many threes are there? 1, 2. Fours 2, fives 2, 6, 1, 7, 2. Okay. So this is the histogram of the image. Now you have to plot the histogram. 0, 1, 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. This is RK and this is NK. So here maximum value is mostly 3. So 1, 2, 3. So for 0 we have value 2. So put a star mark. Next for 1 we have 3. Okay, next for 2 we have 2. For 3 also 2. 4 also 2. 5 also 2. 6, 1, 7, 2. Okay. Like that you have to plot the histogram. Now our aim is you have to modify this histogram. For quality improvement. Okay, it can be done in two ways. First one is histogram equalization. So what is meant by histogram equalization? Means we equalize the histogram. So what are the conditions for that? How can we perform histogram? So to perform histogram equalization, we have to follow some rules. The first rule is, generally we know that S is equal to T of R, right? And R values must be in the gray level range, that is 0 to L minus 1. Okay, right? And S also must be in that range only. Okay, in that range only. Second condition is T of R is monotonically increasing function. T of R is monotonically increasing function. Okay, these two are the basic conditions used for histogram manipulation. And the histogram manipulation probability density function is defined as like this. S is equal to L minus 1 into sigma of Nk by Mn. Okay, Nk by Mn. What does it mean? Or S is equal to L minus 1 into zero to R PR of omega d omega. Okay, this is the definition of histogram equalization. This is for discrete value, this is for continuous image. Okay, now for this we have to define the probability density function, PDF. The probability density function of enhanced image is given as like this. PDF, probability density function, dr by ds. Okay, from this you have to derive the density function. Okay, we know that S is equal to, because we have to check whether the given function is monotonically increasing or not, right? So we know that S is equal to this one. Okay, so now calculate ds by dr. Okay, L minus 1 into dr by r. So derivative integral gets cancelled. So ds by dr is equal to L minus 1 into PR of R, right? PR of R. Now you have to calculate, substitute that one in PSS of R. PR of R into 1 by PR of R L minus 1. So PSS of S is 1 by L minus 1. So if you observe this one, it looks like uniform distributive function, right? Random variable, right? So the output image, the image is uniformly distributed, means histogram is uniformly equalized, so that we can say that the given function is histogram equalized. So how to perform problem? We have only one problem, that is problem in this chapter, that is histogram equalization. So steps to perform histogram equalization. Okay, so what is the definition? S is equal to L minus 1 into sigma and k by total number of pixels, right? So first step, find the histogram of the image. Histogram of the image, that is h of rk is equal to nk, this one. Okay, second one, find the running sum running sum of the image, that is sigma nk. Okay, and third one, divide the running sum with total number of pixels, means sigma nk by mn. Step 4, now multiply with the maximum gray level, that is gray level L minus 1. That implies we get L minus 1 into sigma nk by mn. Sigma nk by mn. So that image is enhanced. Now round off the values with nearest integer. Now replace new gray level values with, now replace old gray level values with new gray level values. So let us see, while doing the problem you can understand this one clearly. Okay, so I am taking one image. R is equal to like this, 1 2 3 4 5. Okay, 3 4 5 4 3, 3 5 5 3, 3 4 5 4 3, 4 4 4 4 4. So it is 5 by 5 image. Okay, 5 by 5 image. So total number of pixels are mn is equal to 5 into 5, that is 25, right? Maximum gray level value, we know that It is 3-bit image because from this image observe here maximum value is 5. For 5 we required 3-bit, right? 3-bit. So 3-bit image maximum gray level value is, for 3-bit image maximum gray level value is 0 to L minus 1, that is 0 to 7. 0 to 7. Now first we have to plot the histogram. We have to calculate histogram. So gray level 0, 1, 2, 3, 4, 5, 6, 7. Right? NK. You have to calculate NK. Step 1. NK. Okay. Number of zeros we don't have here. Number of ones also don't have. Number of twos also don't have. Number of threes 1, 2, 3, 4, 5, 6. 6 are there. Number of fours 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14. Number of fives 1, 2, 3, 4, 5. 6070. Okay, this is step 1. Next step 2, running sum, that is sigma nk. Sigma nk, how we calculate sigma nk? See, this is 0, so we add here. Next 0 plus 0, 0, 0 plus 0. Okay, next 0 plus 6, 6. 6 plus 14, 20. 20 plus 5, 25. 25 plus 0, 25. 25 plus 0, 25. Like this, we perform sigma and k. After performing sigma and k, step 3, we have to divide with the total number of pixels. Here total number of pixels is 25. So 0 by 25, 0 by 25, 0 by 25, 6 by 25, 20 by 25, 25 by 25, 25 by 25, 25 by 25. That means it is equal to 0, 0, 0. 6 by 25 means leave it like that. 24 by 5, 1, 1, 1. Right? 1, 1, 1. Next, step 4. Multiply with L minus 1. L minus 1 into sigma and k in by mn. So 0 into 7. 0 into 7. 0 into 7. 7 into 6 by 25. 7 into 4 by 5. 7 1 just 7, 7, 7. So final values are what? Final values 0, 0, 0. 7 6 42 by 25 is nearly equal to 2. Okay. 7 4 28 divided by 5. So it is nearly equal to 6. So next 7 7 7. Okay. So what is the new intensity values? Old intensity, new intensity values. Okay. Old intensity and new intensity. 0 is 0, 1 is 0, 2 is 0, 3 is 2 now. See, 3 is 2, 4 is 6, 5 is 7, 6 is 7, 7 is 7. Okay. This is the new intensity value. We have to perform like this. Histogram equalization. histogram equalization. So next one is local processing. Okay. Next one is local processing or neighborhood. We call it as spatial filtering. Spatial filtering or local processing or a neighborhood operation. Okay. So the spatial filters are classified into two ways. Smoothing spatial filter, smoothing spatial filter, or we call it a low pass filter. Second one is sharpening spatial filter or high pass filters. High pass filters. So here we define a local mask or filter mask. That mask is using that mask is we perform convolution on the image. Perform convolution on the image so that we enhance the image. So in low pass filter, first one LPF mask, LPF or average filter or mean filter. Mean filter. Mask is defined as small h is equal to 1 by 9. Okay. This is the LPF or basic LPF or average filter or mean filter. And second one is weighted average filter. Small h is given as 121, 242, 121. Okay, you have to remember these filter masks. Okay. Third one, Bartlett filter. Bartlett filter is given as h is equal to LPF convolution LPF. So that is 1 by 9, 111, 111, 111, convolution 1 by 9, 1111, 111. That is equal to 1 by 81, 12321, 24642, 36963, 24642, 12321. That is Bartlett filter. And next, Gaussian filter. Gaussian filter H is given as 1 by root of 2 pi n sigma square two pi n sigma e power m minus m square 2 sigma square into 1 by root of 2 pi sigma into e power minus n square 2 power 2 sigma n square. This is for continuous image. Continuous image. Generally for digital image we have to write the in matrix form. Okay, matrix form is generated using Pascal's triangle, that is 1 1 1 1 2 1 1 2 2 1 1 3 sorry 1 2 1 1 3 3 1 1 4 6 4 1. This is the Pascal triangle. How can we generate Gaussian filter? Gaussian filter of nth order. Nth order means this one. Okay, or row. You have to select this row, n rows. Okay, based on this one, we have to select. So Gaussian filter of nth order is given as 1 by 4 nth row transpose. Nth row transpose. Okay. Sorry, not 1 by 4. 1 by sum of elements of nth row of Pascal triangle. Okay, into nth row transpose. Okay, into nth row transpose into nth row. Nth row. Suppose consider n is equal to 3. So third row of Pascal triangle is 1 to 1. Okay, is 1 to 1. So sum of elements is equal to 4. So 1 by 4 whole square into nth row transpose 1 to 1 into nth row 1 to 1. So 1 by 4 square is 1 by 16. 1 by 16 and the product of these two 1 2 1 2 4 2 again 1 2 1. So this is the final Gaussian filter. Okay, next one is median filter. Median filter is nothing but each pixel is replaced with median of its neighborhood. Okay, each pixel is replaced with its neighborhood. Suppose I am considering one image example 1 2 1 1 3 4 4 5 6. Okay, this is one image. Okay, this is one image. Now we have to calculate neighborhood for each pixel. So suppose this is one pixel. The neighborhood of this pixel is these four only, right? So 1, 1, 2, 3. The median is average of this one. 1 plus 2 by 2, 3 by 2. That is 1.5. Okay, 1.5. 1.5 nearest value is 2. Okay, we replace with this 2. Now for this one, for this pixel, these are neighborhood. So 1, 2, 1, 3, 4. Again we get 1 and 2. So average is 2. Next for this one, 1, 2, 3, 4. 2 plus 3 by 5. 5 by 2, that is 2.5, nearly equal to 3. So this pixel is replaced with 3. Okay. So for this one, neighborhood is this one. 1, 1, 2, 3, 4, 5. I am calculating median for this one, neighborhood. Replaced with median of its neighborhood pixels. So 1, 1, 2, 3, 4, 5. 1, 1, 2 plus 3 by 2. That is nearly equal to 3. This one is 3. Now for this one, 1, 1, 1, 2, 3, 4, 4, 5, 6. So neighborhood is 3. So 3. Next for this one, 1, 2, 3, 4, 5, 6. 3 plus 4, 7 by 2, that is 3.5, nearly equal to 4. Same value. Next for this one, 1, 3, 4, 5. 3 plus 4, 3.5 by 2 means 4 only. Okay, next for this one, 1, 3, 4, 4, 5, 6. 4 plus 4 divided by 2. So 4. This one is replaced with 4. Next this one, 3, 4, 5, 6. 4 plus 5, 9 by 2. 4.5 by 2. So nearly equal to 5. So this one is replaced with 5. So new image is 2, 2, 3, 3, 3, 4, 4, 4, 5. Okay, this is enhanced image using median filter. Means each pixel is replaced with median. Okay, of its neighborhood. Neighborhood means this one bit distance. Unit distance pixels are considered a neighbor, right? Next, spatial filters. Spatial sharpening filters. Spatial sharpening filters. So in spatial sharpening filter, we have defined as h is equal to, first one is 1 by 9 minus 1 minus 1 minus 1, 8 minus 1 minus 1 minus 1. So this is one of the high pass filter. High pass filter. Second one is unsharp masking. Unsharp masking steps. First one is blur the original image. So if you blur the original image, what we get? Low pass filter, right? Low pass filter. Now subtract blurred image from original. Okay, so that we get G mask is equal to F minus F cap, F dash. Okay, now sharpen image, sharpen filter is given as S is equal to F plus K star G mask, where K is some constant or weight. K is weight. If K is equal to 1, we called unsharp masking. Unsharp masking. K is greater than 1 means we referred as high boost filtering. High boost filtering. Okay. Next, last one is global processing. Global processing. So global processing, in that we have to define linear one. Linear means image negative. Image negative. Image negative is defined as S is equal to L minus 1 minus R. The graph is represented like this. This is R, this is S. Okay. L minus 1, L minus 1. That is 0. Image negative. Second one is logarithmic. Logarithmic. Logarithmic is given as S is equal to some constant into log of 1 plus R. Log of 1 plus R. This is the graph. L minus 1, L minus 1, 0. Next, exponential. Exponential. So S is equal to C into E power R. Okay. The graph is like this. Okay. R S. Next, power law. Power law or gamma transformation. Power law or gamma transformation. So S is equal to C into R power gamma. R power gamma. So according to this gamma, the image will be varies. Enhancement is varied. Okay. Gamma is equal to 1. Gamma less than 1. Gamma greater than 1. Okay. S R S. Okay. Next, contrast stretching. Contrast stretching is defined with this function. So this is directly graph. Okay. For transform function, we have directly graph. Okay. R2 comma S2, R1 comma S1. We have 2 points. By varying these 2 points, we perform contrast stretching. So here we have 2 conditions. Okay. We have 3 cases. First case is if R1 is equal to S1 and R2 is equal to S2. Okay. Then transformation function. This is T of R. transformation function is linear. Is linear. Second case, if R1 is equal to R2, R1 is equal to R2, and S1 is equal to 0, S2 is equal to L minus 1, then T of R becomes thresholding function. Thresholding function. Okay. And third one, if R1 less than or equal to R2, S1 less than or equal to S2, then T is single value and monotonically increasing function. Increasing function means it will increase only, doesn't decrease or doesn't bend to 0. Okay. Once it is increasing means it will follows increasing only. Okay. Next, sixth one, intensity slicing. Intensity slicing. So here we have two ways. Without preserving background. Without preserving background. So S is equal to L minus 1 between two values, and otherwise 0 means this is the function R S A B. This is L minus 1. Second one is with preserving background. With preserving background. So it is given as S is equal to L minus 1. Remaining time original image only. We don't put 0. That is the difference. Okay, remaining time we put input image only. So then the graph is looks like this. R S. This is A. This is B. Okay. Next, last one is bit plane slicing. Okay, bit plane slicing. Generally, if you consider 4-bit image, so consider 3-bit image, so that we get gray level values up to 0 to 7, right? 0 to 7. 3-bit image means we get gray level values are 0 to 7. Okay, 0 to 7. So how many bits are there? 3 bits. The numbering are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 111. Okay. So this is one plane. This is one more plane. This is one more plane. So each bit is considered as one plane. We represent it like this. Okay, 3 planes. One plane. Okay, like this we represented 3 planes. 4-bit means 4 planes. 8-bit means 8 planes. So what we doing here? Suppose, okay, based on the number of pixels, okay, based on the number of pixels, suppose I am considering one image, 1, 1, 2, 3, 4, 1, 1, 2, 3. So for this image, how many pixels are there? 9 pixels are there, right? 3 by 3. So 1 means 0, 0, 1. Okay. Next for 2, 0, 0, 1. 0, 1, 0. 3 means 0, 1, 1. Again 3. Next 1. Next 2. Next 3. Observe here. The first plane has ones. Second plane also has ones. Third plane does not have any single one also. So if you remove this one plane, if you remove this plane, what we have? We get only 2-bit, right? We have only 2-bit. And the maximum range is what for 2-bit? 0 to 3. 0 to 3. Generally here 7 represents white color, right? White color. 3 represents gray color, right? Gray color. Some gray color, 0 to 7. But now if you remove third plane, because there is no ones for this image. So if you remove third plane, we get only 2 planes. For these 2 planes, we consider as 2-bit. 2-bit means the range is 0 to 3, right? 2-bit means the range is 0 to 3. Now 3 becomes white color. White color means what happened? The brightness is modified from gray to white color. Gray to white color means we are increasing the contrast or brightness of the image. Okay, increasing the contrast or brightness of the image. So this is global processing techniques. Now enhancement in frequency domain. Enhancement in frequency domain. So in frequency domain, what we have to do is, step 1 is pre-processing. Okay, pre-processing means capturing of the image, anything. So for pre-processing, we apply image transform. Image transform. For after transforming the image, so that we get frequency domain. So for this frequency domain, we perform filtering operation h of u comma v. So filters may be low pass or high pass or band pass. After applying, we perform inverse image transform. Again, we perform post processing so that we get enhanced image, input image, or enhanced image S. Okay, this is the steps involved in frequency domain. So here we have to learn about these filters. Okay, low pass filter or also known as smoothing filter. Next, high pass filter, HPF, or sharpening filters. So high pass filter is simply given as 1 minus LPF. Okay, 1 minus LPF. If you learn the low pass filter, we get high pass filters. So in low pass filters, we have ideal low pass filter. Ideal low pass filter is defined as h of u comma v is equal to 1 for d of u comma v. This is frequency component, cutoff frequency. If d of u comma v is greater than d naught. So this is ideal low pass filter. Now ideal HPF is given as 1 minus low pass filter, right? So 1 minus 1 means 0. If d of u comma v is less than or equal to d naught, this is 1. For d of u comma v is greater than d naught. Okay, this is ideal low pass filter. Next, Butterworth low pass filter. So Butterworth low pass filter is given as h of u comma v is equal to 1 by 1 plus d by d naught whole power 2n. This is Butterworth. For high pass, Butterworth ideal LPF, Butterworth LPF. H is given as this one. So Butterworth HPF. H is given as 1 minus this one. So after solving this one, we get 1 by 1 plus d naught by d whole power 2n. Okay, whole power 2n. Next, Gaussian LPF. H of u comma v is equal to e power minus d square by 2 d naught square. Next, Gaussian HPF. H is equal to 1 minus e power minus d by 2 d naught square. Okay, this is the low pass and high pass filters in frequency domain. Okay.